Dear students, now we are going to discuss about Schrodinger wave equation. So in this video, I would like to derive time independent wave equations. So before derive this time independent wave equation, we must know the introduction part for the Schrodinger wave equation. So to understand this Schrodinger wave equation, we have to learn about the de Broglie hypothesis. So in this previous video, I have given this de Broglie hypothesis. Please watch that video and then come and listen this Schrodinger wave equation. So that video link I have given in the description box. Okay, so let us enter into our topic Schrodinger wave equation. So what is meant by Schrodinger wave equation? So in this content we are going to discuss 6 things. First one is what is the introduction, and then what he considered to derive the wave equation, and what is meant by wave function, types of wave equation, and then time independent wave equation, the full derivation part, and the special cases of its result. Actually, this is what we are going to discuss in detail. Alright, so let me start the introduction part. So what is meant by Schrodinger wave equation? So actually de Broglie has given the wave nature of particle. Okay, he explained how the particles are behaving, that waves behaving as a waves. So the same statement Schrodinger has given the mathematical form. So Schrodinger describes the wave nature of particle in mathematical form, and this equation is known as Schrodinger wave equation. It is one of the most fundamental equations of quantum physics. This is basically a differential equation and widely used in chemistry and physics to solve problems based on the atomic structure of the matter, right? And it is a mathematical expression describing the energy and the position of electron in space and the time. So he mentioned that that means the electrons are having the wave nature. Okay, electron is having the dual nature. Based on that concept only, he derived this mathematical expression to describe the energy and the position of electron in space and time. Okay, so this is what the small introduction about Schrodinger wave equation. That is, he had considered that the wave nature of the electron, wave nature of particle in mathematical form. He describes in the mathematical form, in equation form. That's what it is known as Schrodinger wave equation. So to derive this wave equation, he considered 3 points. So what is the consideration? Let us see now. So he considered 3 points. What is that? First one, he considered de Broglie's hypothesis. So de Broglie hypothesis, this is the wavelength. Lambda is equal to h by mv. Here h is the Planck's constant and m is the mass and v is the velocity of the moving particle. Okay, this is the first consideration. And the second one is classical differential equation of wave system. That means already in classical physics they have derived some sort of equations to explain the wave nature. Okay, wave nature of the system. So that equation directly he considered to derive the Schrodinger's wave equation. That equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square, which is equal to 1 by v square into dou square psi by dou t square. Here psi is nothing but wave function. Psi is nothing but wave function. Okay, so later I will explain what is this wave function and what is the definition for that. And the third thing what he considered is conservation of energy. That is, total energy is equal to kinetic energy plus potential energy. So the formula for kinetic energy is half mv square and potential energy is capital V. So here V is the velocity of the particle and capital V is the potential energy of the particle. So the total energy is represented by E. So these 3 points he considered and finally he reached the Schrodinger wave equation. Okay, so next, what is mean by wave equation? Just now I said in the classical differential equation he used the symbol this. So this is represented as psi. Okay, P is silent. So we have to pronounce it as a psi. So what is this psi? It is a variable quantity that is associated with moving particle. If the particle is at rest, means there is no variable quantity. If the particle is moving, then only the variable quantity will be associated with it at any position and a time. At any position and a time. And it relates the probability of finding the particle at the space and time, at the point and time. So which is nothing but it explains the amplitude of the wave. Okay, which explains the amplitude of the wave. So as you know well, amplitude is nothing but the maximum displacement from the mean position. So the wave function is nothing but amplitude of the wave for our understanding. And next, there are two types of Schrodinger's wave equation. One is time dependent wave equation and another one is time independent wave equation. So in this video, we are going to derive time independent wave equation, right? So now let us get into the video. Time independent wave equation. So already I said that he considered three things. First one is lambda is equal to h by mb. So this is de Broglie hypothesis. So based on de Broglie hypothesis, the wavelength lambda is equal to h by mb. And the next one is classical differential equation for the planes for the wave system. Classical differential equation for wave system. For wave system. So what is that equation? Dou square. This is the partial differential equation. That's what dou square psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square, which is equal to 1 by v square into dou square psi divided by dou t square. So this is the classical differential equation. Okay. So here actually in equation 1, lambda is equal to h by mv. Lambda is the wavelength of the particle and h is the Planck's constant, m is the mass of the particle and v is the velocity of the particle. Likewise, here psi is the wave function. Psi is the wave function and then x, y, z are the coordinates of the particle. Coordinates of the particle. And next, v is the wave velocity, and the small t is the time. Small t is the time. Okay. This is second equation. Explanation about the second equation. Okay. And then he combined these two and trying to solve the time independent wave equation. So the next step is, here you see in the second equation, dou square by dou x square. Here psi is common everywhere. So I am going to take the psi outside. So how can I write the second equation? Please follow this. See, within the bracket, dou square divided by dou x square plus dou square divided by dou y square plus dou square divided by dou z square. I have taken this psi outside from this bracket, which is equal to 1 by v square into dou square psi divided by dou t square. Right? So for this bracket, I am going to introduce one operator, which is del square. Okay, for this bracket. So del square psi is equal to 1 by v square into dou square psi divided by dou t square. So this I am considering equation number 3. Here, where del square is equal to, what is the value of del square? This bracket, dou square divided by dou x square plus dou square divided by dou y square plus dou square divided by dou z square, which is named it as Laplacian operator. Laplacian operator. Laplacian operator, right? So this is the second order differential equation, right? The equation 3 is the second order differential equation. So now I am going to get the solution for this equation 3. So listen carefully. The solution of equation 3 gives the periodic displacement, that is wave function, periodic displacement or amplitude. Okay, the periodic displacement in terms of t, in terms of t, right? So what is that solution for this equation? Directly I am going to write the solution for this equation. So psi, which is equal to psi naught into e power minus I omega t. Okay, psi is equal to, psi is the wave function, which is nothing but the amplitude of the wave or periodic displacement, any name we can use for that, which is equal to psi naught into e power minus I omega t. Here psi is the x, y, z, is the function of position and time. Okay, psi is the function of position and time, and psi naught is only the function of position, not of t. That will be the difference. Listen carefully. So psi is the function of position and time, but psi naught is the function of only position. So what is meant by psi naught? The psi naught is the amplitude of the wave at a particular point considered. Okay, so this I am considering equation 4, and I will write what is meant by psi naught. So now psi naught is the amplitude at the point considered. At the point considered. It is not the function of t. That is very important. It is not the function of t. It is only the function of position. That's what I have mentioned. X, Y, Z. Okay, not a t. I didn't mention the t. So what is the meaning of that? It is only the function of the position, not of time t. Right? Okay. So now I'm going to differentiate that wave function to get the result. So see here. Equation 4. What is the equation 4? Psi is equal to psi naught e power minus I omega t. I am going to differentiate this equation twice to get the value of dou square psi by dou t square. Okay. So listen carefully this step. Once again, I will write this equation 4 for your reference. So equation 4. What is this? Psi is equal to psi naught into e power minus I omega t. Okay, what I'm going to do? Differentiating, this is equation 4 already I mentioned. So differentiating the above equation, twice. This is very important. Twice with respect to time. Okay, differentiating the above equation twice with respect to time. So what we will get, listen here. So first I am differentiating this value. So dou psi by dou t, right? Once I differentiated dou psi by dou t with respect to t, right? And then already I said psi naught is only the function of position, not of time t. So it is the constant, as such I am going to write. And then if you differentiate this e power minus I omega t, we will get minus I omega. Okay, if you differentiate this, so e power minus I omega t again. So one time we differentiated. Already I mentioned twice we have to differentiate. So the same equation to be differentiated again. So what will happen? Dou square by dou t square. Dou square by dou t square, which is equal to, again psi naught will be same and minus I omega will be same. If you differentiate this part again, it will become minus I omega, then e power minus I omega t. Okay, so if you differentiate twice, we will get like this. So here I am going to solve. Minus into minus become plus, right? I into I become I square, and then omega into omega become omega square, and then what is that? Psi naught e power minus I omega t, right? So see here, I is the complex number. So here I will write I is the complex number. What is the value of I square? I square is equal to minus 1, as we know well. I square is equal to minus 1. So here minus 1, okay, omega square, okay, psi naught e power minus I omega t. See here psi naught e power minus I omega t. So which is equal to psi. So instead of this part I am going to write psi here. So in short form minus 1 into omega square become minus omega square psi. Minus omega square psi, which is the value of dou square psi divided by dou t square. Dou square psi by dou t square. So this I am considering equation number 5. This I am considering equation number 5. Okay. So now we are going to the equation 3. Okay. So I am going to substitute this value equation 5 in equation 3. Okay. What is equation 3? Once again I will show you. This is equation 3. So del square psi is equal to 1 by v square into dou square psi by dou t square. In equation 5 we solved this bracket. Okay, so that value I am going to write here. So the equation 3, substitute equation 5 in equation 3. Okay, so what is equation 3? Del square psi is equal to 1 by v square into minus omega square. Actually, the value of dou square psi by dou t square is equal to minus omega square into psi. Okay, so here I am going to write like this, minus omega square divided by v square into psi. Okay, the next step, del square psi, this minus symbol I am going to take into this side. So plus omega square divided by v square into psi is equal to 0. Okay, so this I am considering equation number 6. I am considering equation number 6. Okay, the next step we have to find out the value of omega square divided by v square. So for our reference I will write like this, to find omega square divided by v square. Omega square divided by v square. So here what is omega actually? Omega is the angular frequency. What is omega? Angular frequency. So there is one relation between angular frequency and the linear frequency. That is omega is equal to 2 pi nu. 2 pi nu. So here 2 pi and nu is the linear frequency. This is the relation between the angular frequency and the linear frequency. Now I am going to do small modification. Listen carefully. As we know the formula, velocity of the light c is equal to nu into lambda. Nu is the frequency, lambda is the wavelength. Actually here we are talking about the velocity of the wave. So velocity of the wave is represented by v. So v is equal to nu into lambda. V is equal to nu into lambda. I need a nu here. So nu is equal to V by lambda. Nu is equal to V by lambda. So here in the place of nu, I am going to substitute V by lambda. So next step what I can write, 2 pi in the place of nu, I am going to write V by lambda. So what value we need? Omega by V. So here omega is there. V is this side. Bring to this side. So omega divided by V is equal to 2 pi divided by lambda. 2 pi divided by lambda. But we need the square of it. So the next step, you square it. Okay. By squaring, so what will happen now? Omega square divided by V square is equal to 2 pi by lambda. Okay. So 2 pi divided by lambda the whole square, right? So how can we write 4, 2 square become 4, 4 pi square divided by lambda square. So this is equation number 7. So what we can do? Substitute the value of omega square by v square in equation 6. In equation 6. So what is equation? That is value of the equation 7 in equation 6. So what is equation 6? Del square psi plus omega square by v square. What is the value of that? 4 pi square divided by lambda square into psi is equal to 0. So from the first equation, what is the lambda? De Broglie wavelength. So equation 1 is nothing but lambda is equal to h by mb. Lambda is equal to h by mb. We need the square value of that. By squaring, lambda square is equal to h squared divided by m square v square. So substitute this value in this equation. So how to write? Del square psi plus 4 pi square. Okay, so lambda square means this will h square divided by m square and v square, so it will go up. So m square v square into psi is equal to 0, into psi is equal to 0. So this I am considering equation number 8. Okay, till now we used only two considerations, that is de Broglie wavelength and classical wave equation. So next I am going to consider the conservation of momentum. Okay, so what is the conservation of momentum formula? Total energy is equal to kinetic energy plus potential energy. So the third one, this is very important, conservation of energy. Conservation of energy. So according to that, we have discussed total energy is equal to kinetic energy plus potential energy. So total energy is represented by E. Kinetic energy is half mv square plus capital V is the potential energy. I am going to consider this V to this side. So E minus V is equal to half m v square. So now this 2 also I am going to multiply here. So 2 into E minus V is, sorry, capital V, differentiation should be there. Half m small v square. Sorry, half will not come. Already that 2 I multiplied here. So only m v square, right? So multiply m on both sides. On both sides. So what will happen here? 2m I am multiplying. So 2m into E minus V, which is equal to m into m become m square v square. Okay. So now you see m square v square value. So that is what we considered in the equation 7. Now you see in the place of m square v square, I am going to substitute that value. Okay. So the next step is, I will write in the next page. Substitute the above equation in equation 8. In equation 8. So what is that equation? Del square psi plus 4 pi square. In the place of m square v square, what we have to substitute? 2m bracket E minus capital V. Okay, this is the m square v square value, whole divided by h square into psi is equal to 0. So 4 into 2, I'm going to multiply here. So del square psi plus 4 into 2 become 8 pi square m E minus V divided by h square into psi is equal to 0. So this is what Schrodinger's time independent wave equation. Now you see this equation, the first term is del square psi. So del square is the Laplacian operator and psi is the wave function. 8 is the numerical number, pi is the constant, m is the mass of the particle, and E is the total energy of the particle, and V is the potential energy, and h is the Planck's constant. Wave function, psi is the wave function. So in this equation there is no time. Okay, there is no time variable. Okay, that is the reason it is named it as Schrodinger time independent. Okay, time independent wave equation. Time independent wave equation. So this is the final result. Time independent wave equation. Okay, I hope you understand the steps. Okay, please go through it. And next, I would like to discuss the special cases for the result. Okay, the special cases for this one. So what are the special cases? special cases of our result. Actually, we have discussed this equation for 3 dimension. Suppose we are going to write for 1 dimension. Okay, how the equation will be modified. Okay, so if the particle is moving along 1 dimension, how this equation will be considered. Okay, the 1 dimension is in the sense along x-axis, along x-axis. So instead of del square psi, I am going to write only dou square psi by dou x square only along x-axis. Okay, so that 8 pi square m into e minus v divided by h square into psi is equal to 0. Okay, so the same equation only, but in terms of x-axis I have mentioned. Okay, so this x here I can represent. Psi of x means that particle is moving only along x direction. Okay, this is the one result. And the next result in terms of reduced Planck's constant. Reduced Planck's constant. So what is this reduced Planck's constant? Already we know that Planck's constant is h. Okay, so reduced Planck's constant is represented by h bar or h cross. Okay, h cross. H cross is equal to h by 2 pi. H cross is equal to h by 2 pi. So in place of h by 2 pi, I can represent h cross. So if you square it for our convenience, if you square, h cross square is equal to square this side also, h square divided by 4 pi square. Right. So now how this equation will change? That is the main equation. So del square psi plus here 2 pi square is there. So how can we divide? 2 into m will come outside. So how can we write 4 pi square divided by h square into e minus v capital V into psi is equal to 0. So for this 4 pi square by h square, I can able to write h cross. So how can I write del square psi plus 2m for this place e minus v divided by h cross square, okay, into psi is equal to 0. Okay, so this is what the second one in terms of reduced Planck's constant. So reduced Planck's constant is represented by h cross. So del square psi plus 2m by h cross square into e minus v into psi is equal to 0. This is the another case. And the third case is for a free particle. If the particle is moving freely, there won't be any potential energy. So the potential energy V is equal to 0 for this case. So how the equation will change now? Del square psi plus 2m, actually e minus v, but v becomes 0, so that e divided by h cross square into psi is equal to 0. Okay, so this equation is for free particle, okay, so this is what the third special case. So up to that we have discussed about time independent wave equation. Please go through that. If you have any doubt regarding this, you can ask in the comment box. So thank you everyone.